Hello, today I'm going to derive the formula for Shannon's entropy using some common example. You have like a roulette with a ball. The probability for the ball to land in one of the K packets can be uh, like this. We can use something known as multinomial distribution because there are more than two possible outcomes. There are here k outcomes. Therefore, we can use something known as multinomial distribution with random variables. For example, we have these random variables x1, x2 until xk. These are known the random variables, and the occurrence in our case is A, the first occurrence for the outcome number 1, and second occurrence for outcome number 2, and until we go. The number of independent trials is the summation of all the occurrences. Using the formula, in our case, using the formula, we can say that the n factorial over x 1, which is in our case is a, which is the number of occurrences, or we can say that of the first outcome factorial, and then multiplied by the probabilities to the power of the occurrences. We must so this equation must satisfy two conditions. The first condition is that the sigma from y equal 1 to the k, where k in our case is the number of possible outcomes, is equal to the number of independent trials, and the sum of the total probabilities is 1. Therefore, we can use this formula. Using the formula from the previous slide, we can substitute our values in this formula. We can get this using also the assumption that the k, the n independent trials, is equal to the sigma from y is equal to 1 to k of ar. Using the fact that the probability is equal to 1 over k, where k is the number of possible outcomes, we can substitute this in our equation, and using these two conditions, we can substitute in our equation n factorial over a1 factorial, a2 factorial, a3 factorial into a k factorial, and which is 1 over k. Yes, therefore to all of the probabilities there are 1 over k. Or 1 over k, so p1 is equal to 1 over k, and p2 is equal to 1 over k, so we can simply say this is equal to 1 over k dot a1 plus a2 plus a3 plus a until we reach a k. Using the assumption, we can say that this is exactly equal to n factorial over a1 factorial, a2 factorial, a3 factorial, to the ak factorial with 1 over k to the power of n, where n is the total number of independent trials. This is can be written as omega over t, which is the same as p. So the probability is this, which can be written as omega. Always the probability is in the form of a fraction, where omega means is the number of desired outcome divided by the number of total outcomes. So the number of desired outcome divided by the number of total outcomes, right? So in our case, we can say that t is equal to n to the power of p is the number of all possible outcomes for a set of p. Okay, we must know that the entropy of the distribution is h is equal to log sigma, which is the same as log p factorial over in our case our sigma in our case is n factorial over a1 factorial a2 factorial until ak factorial. This can be written as log n factorial minus log a1 factorial minus log a2 factorial until minus log ak factorial. We must use the rule for logarithm, that's log x, y, z is equal to log x plus log y plus log z. Therefore, you can say that this is the same as sigma y is equal to 1 till n log I minus sigma from y is equal to 1 a1 log I minus sigma from y is equal to 1 a2 log I till minus 1 k log I, right? The summation can be approximated using the integrals. This will be discussed in the next slide. Therefore, the entropy can be represented using this equation. We must know the rule for the integral of logarithm. Integral of logarithm is simply x log x minus the integral of x minus the integral of x dx over x, simply using the integration by parts uv minus integral v du, which is this becomes x log x minus x. This is a quick recap of the integral of logarithms. Therefore, h is equal to h can be written as using the formula by substituting, which is n log n minus n plus 1 minus a1 log a1 minus a1 plus 1 minus a2 log a2 minus a2 plus 1 until minus a2 log minus ak log ak plus 1, using of course brackets in our case. Therefore therefore this can be simplified as n log n plus 1 minus a1 log a1 plus 1 minus until ak log ak plus 1, because you can see that you can notice that in our case sigma here is minus n and here is plus. Using these terms will cancel out. We are left with these terms. Therefore, we can write h as n log n minus sigma from we can write from y is equal to 1 till k of a k log a subscript k plus 1 minus n. We can use some here algorithm by letting for example m I is equal to a I ak nk is equal to ak over n. Using this algorithm, using this assumption, this equation will be reduced a lot. So we can continue. This becomes n log n minus sigma from I is equal to 1 to k of ni dot n of log ni dot n plus 1 minus n becomes n log n minus sigma from I is equal to 1 to k of ni n of log n dot log n plus log like this plus 1 minus n. Therefore h will become 1 like this becomes 1 minus n. One second, have in our case n here I made an error. It must be here k instead of n. Therefore 1 minus sigma from I is equal to 1 till k of n log m and I. Therefore, h can be written as minus sigma. The term 1 minus k can be dropped since it is independent of the distribution. So this can be minus I is equal to 1 till k of p I log p I. So here's the proof for the equation. Thus this also relates to Boltzmann distribution, which says that S is equal to K ln omega. So we can verify that our proof is correct. Also, there was some redundant error in our equation. This must be pi instead of ni. Therefore, this. So our equation like gives us the Shanon entropy, which is negative sigma pi log pi, which can be written as negative is equal to sigma I is equal to 1 to k of pi log 1 over pi. This exactly our Shanon entropy formula derivation. Goodbye.